episode 113, titled SVD and Nearest Neighbors, where they appear in DataX scenarios. We focus on two ideas that show up everywhere in applied data work because they are building blocks rather than flashy end products. Singular value decomposition, abbreviated as SVD, is a way to break a matrix into simpler pieces that reveal latent structure and support compression. Nearest neighbors methods, often shortened to neighbors or KNN, are a way to make predictions or retrieve items by looking at what is most similar under a chosen distance metric.
These techniques appear in many DataX-style scenarios because they are practical, general, and easy to embed inside larger systems.
The exam angle is usually about recognizing when each method is appropriate, what assumptions it relies on, and what practical pitfalls can cause misleading results. If you treat SVD and neighbors as tools for representation and similarity rather than as mystical algorithms, their use cases become obvious.
This episode builds that recognition so you can choose them confidently and explain them without overclaiming meaning.
Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. SVD is a matrix decomposition technique that breaks a matrix into orthogonal components that are easier to analyze and manipulate. Conceptually, it expresses a matrix as a product of three matrices, where one captures orthogonal directions in the original row space, one captures orthogonal directions in the original column space, and the middle diagonal structure captures the strength of each component. You do not need to memorize the exact form to understand the core idea, which is that SVD identifies patterns in a matrix that can be represented as a weighted sum of a few dominant modes. Each mode represents a coherent structure linking rows and columns, such as common covariation patterns, while the associated strength tells you how important that mode is for reconstructing the original matrix. Because the components are orthogonal, they provide a clean basis for representing the matrix in a simpler coordinate system. This makes SVD a foundation for compression and for understanding latent relationships in data. In exam terms, the key definition is that SVD decomposes a matrix into simpler orthogonal components that capture structure. SVD is widely used for compression because you can approximate the original matrix using only the strongest components, which reduces dimensionality while preserving much of the signal. If you keep only the top components, you reconstruct an approximation that captures the dominant patterns and ignores weaker components that often represent noise. This is also why SVD supports denoising, because noise tends to spread across many small components rather than concentrating in a few strong ones. When you truncate the decomposition, you effectively smooth the matrix, keeping consistent structure and discarding small, unstable variations. SVD can also reveal latent structure, meaning underlying factors that explain covariation across rows and columns, even when those factors are not explicitly represented as features. In text, this can uncover themes across documents and terms, and in recommendation, it can uncover preference dimensions linking users and items. The practical takeaway is that SVD turns a large, noisy matrix into a smaller, structured representation that is easier to learn from and reason about. Connecting SVD to principal component analysis, abbreviated as PCA, helps because they are closely related ideas expressed in different framing. PCA is often described as finding variance-maximizing directions in a dataset, while SVD is described as decomposing a matrix into orthogonal components. When you apply PCA to a centered data matrix, the principal components can be obtained through an SVD of that matrix, meaning the same underlying linear algebra supports both methods. The difference is often in what you emphasize, with PCA focusing on variance directions and feature space rotation, and SVD focusing on matrix factorization and low-rank approximation. In practice, both approaches can be used for dimensionality reduction, compression, and noise reduction, and the choice of language depends on whether you are thinking in terms of a data set of observations or a matrix of interactions. Recognizing this relationship helps you avoid treating them as unrelated methods and helps you translate exam questions that frame the same idea differently. The exam usually rewards knowing that SVD and PCA are connected, even if you do not derive the mathematics.
Nearest neighbors refers to the idea of finding similar items or cases by measuring distance or similarity in a feature space, and then using the closest examples for prediction or retrieval. The basic operation is that for a given query point, you compute distances to other points, identify the k closest ones, and then use their labels or values to make a decision. This is a simple but powerful idea because it does not require an explicit model of the relationship between features and targets. It relies on the assumption that similar inputs tend to have similar outputs. That assumption is often reasonable when the feature space is well designed and captures the aspects of similarity that matter. Nearest neighbors methods can be used as baselines, as production solutions in some settings, or as components inside more complex systems. The key is that neighbor relationships depend entirely on the chosen distance metric and feature scaling, which means the method is only as good as its definition of similarity. When you understand neighbors as predict by similarity, you immediately see both the appeal and the risks.
KNN, short for K nearest neighbors, is a specific method that uses the K closest examples to perform classification, regression, or retrieval. For classification, it often predicts the majority class among the neighbors, sometimes weighting closer neighbors more heavily. For regression, it often predicts an average of neighbor target values, again possibly distance-weighted. For retrieval, it returns the neighbors themselves as the output, which is useful when the goal is to find similar cases rather than to produce a numeric prediction. KNN is attractive because it is simple and can work well when the data contains clear local neighborhoods that correspond to similar outcomes. It also serves as a useful sanity check, because if a sophisticated model cannot beat a well-tuned neighbor baseline, the problem may be feature representation or label quality rather than algorithm choice. The trade is that KNN can be sensitive to noise and to how distance is defined, which makes careful pre-processing essential. At exam level, remembering that KNN predicts using the closest examples under a distance metric is the core concept.
Nearest neighbors ideas power recommendation, anomaly detection, and similarity search, because many of these tasks can be framed as finding items most similar to a query or to a user profile. In recommendation, you might find similar users and suggest items they liked, or find similar items and suggest items similar to what a user already engaged with. In anomaly detection, you might treat points that are far from their neighbors or that have low neighborhood density as unusual, which aligns with the idea that anomalies do not belong to dense regions of normal behavior. In similarity search, you might retrieve the most similar documents, images, or events to support investigation and triage, which is common in security workflows where analysts want comparable incidents or behaviors. These uses highlight that neighbors are not only about classification, but about retrieval and exploration. They also show why distance metric choice is so critical, because the method's output is entirely determined by what it means to be close. In DataX scenarios, neighbors often appear as practical components for search and grouping, rather than as standalone supervised learners.
Distance metrics must be chosen carefully because scaling and feature selection can change neighbor relationships dramatically. If features are not scaled and one feature has a much larger numeric range, that feature dominates distance calculations, effectively deciding what similar means, whether you intended it or not. Choosing between Euclidean-style distances, cosine similarity, or other measures also changes the meaning of closeness, especially in sparse high-dimensional spaces where angle can matter more than magnitude. This is why preprocessing choices like normalization are not optional details for neighbor methods. They are part of the model definition. In practice, you validate neighbor behavior by checking whether retrieved neighbors look genuinely similar under domain understanding, not just under the metric. Distance choice also matters for interpretability, because stakeholders may ask why two cases were considered similar, and the answer depends on which features and scales dominated the distance. The exam expects you to recognize that neighbors are geometry dependent, and geometry is defined by scaling and metrics. KNN tends to struggle in very high-dimensional settings because distances can become less meaningful, a phenomenon often described as distance concentration. When many dimensions are noisy or irrelevant, points can become similarly distant from each other, making neighbor distinctions weak and unstable. In sparse high-dimensional spaces, a naive distance metric can be dominated by shared zeros or by random variation, producing neighbors that are not semantically similar. This does not mean neighbors are unusable in high dimensions, but it does mean you often need dimensionality reduction, feature selection, or similarity metrics suited to the data type to make the neighborhood structure meaningful. It also means that neighbor methods can be sensitive to the curse of dimensionality, where the amount of data needed to populate neighborhoods grows quickly with dimension. Recognizing this limitation prevents you from applying KNN blindly to high-dimensional feature sets and expecting it to behave well. The exam often tests this by asking why KNN can degrade as dimensionality increases. Compute cost is a practical constraint for neighbors methods because inference often requires comparing a query to many stored examples. Unlike models that compress knowledge into a fixed set of parameters, KNN stores the dataset and does most of its work at prediction time. This can be expensive when the dataset is large and when real-time latency requirements are strict. There are strategies to speed up neighbor search, such as indexing structures and approximate search, but the fundamental cost trade remains. Neighbors shift computation from training to inference. This matters in operational settings like security monitoring, where predictions must be made at high throughput because expensive similarity search can become a bottleneck. Cost also includes memory, because storing feature vectors for many examples can be large. The exam level point is to recognize neighbors as potentially expensive at inference, even if training is trivial. When you mention this trade-off, you show that you are thinking beyond algorithm names and into deployment realities. SVD often appears in recommender scenarios through sparse interaction matrices, where rows are users, columns are items, and entries represent interactions such as ratings, clicks, or purchases. These matrices are typically sparse because most users interact with only a tiny fraction of items, which makes direct modeling challenging. SVD can be used to factor the matrix into lower-dimensional latent factors for users and items, producing compact representations that capture preference structure. Once users and items are represented in a shared latent space, recommendations can be made by matching users to items with high predicted affinity, which is essentially a similarity computation in latent factor space. This approach also helps with noise and missingness, because the low-rank approximation fills in a smooth structure rather than relying on sparse raw counts. In DataX-style reasoning, this is a classic example of using SVD to discover latent structure and then using that structure for prediction and retrieval. The key is that SVD turns sparse interactions into dense factors that generalize.
Communicating outputs should emphasize similarity and latent factors rather than direct causation, because both SVD and neighbors describe patterns of association, not causal mechanisms.
A latent factor discovered by SVD can be useful for prediction, but it does not necessarily correspond to a real-world cause or a human interpretable attribute unless validated and interpreted carefully. A neighbor-based recommendation that says users like you also liked this item does not mean one item caused the other. It means the interaction patterns are similar. Overstating causation can lead to bad policy decisions, such as assuming that changing one variable will produce the same effect implied by the model's structure. The responsible framing is descriptive. These items are similar under the learned representation, and these factors capture covariation patterns that help reconstruct the matrix. This framing also supports governance because it keeps claims aligned with what the methods actually compute. In exam terms, emphasizing association rather than causation is a consistent theme across unsupervised and similarity-based methods. The anchor memory for episode 113 is that SVD finds latent factors and neighbors find similar cases. Latent factors are the low-dimensional components that summarize the main structure in a matrix, supporting compression and prediction through shared representation. Similar cases are the nearest examples under a distance metric that you use to infer labels, values, or recommendations. This anchor captures the core function of each method and makes it easy to decide which fits a scenario. If the problem is about compressing a large, sparse matrix and uncovering hidden dimensions of variation, SVD is a natural tool. If the problem is about retrieving similar instances or making predictions based on local similarity, neighbors methods are a natural tool. Keeping this anchor in mind helps you answer exam questions that ask you to choose between these building blocks quickly.
To conclude episode 113, titled SVD and Nearest Neighbors, Where They Appear in DataX Scenarios, choose SVD or KNN for one scenario and justify it based on data shape and constraints. If you are building a recommender from a large, sparse user item interaction matrix, SVD is a strong choice because it compresses the sparse matrix into latent user and item factors that generalize and support efficient matching. The justification is that SVD discovers low-rank structure and provides a compact representation that can make recommendations without scanning all raw interactions. If instead you need a simple retrieval system that finds past incidents similar to a new incident report for analyst triage, KNN is a strong choice because it directly returns similar cases under a chosen similarity metric. The justification there is that neighbor search aligns with the decision need of finding comparable examples, though you must manage scaling and inference cost. Being able to justify the choice in terms of latent structure versus local similarity shows you understand these methods as practical building blocks rather than as isolated algorithms. When you can state that clearly, you meet the exam-level expectation for this topic. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.